module we will discuss a concept known as phase velocity and another concept known as group velocity. We have not really talked about these two terms in the earlier lectures because I was waiting for waveguides part to be completed, so that we may have a better understanding of what phase velocity means and what group velocity means. Now, we recall that plane wave which may be polarized along say x or y direction and propagating along z direction would carry energy with it, and the steady state solution, that is when all the transients have died down, the electric field for a x polarized wave can be written as by giving its x component and propagating along z as of a particular frequency omega 0 as some constant E0 e to the power j omega t minus beta z. If the medium is free space and lossless, unbounded, free space is vacuum. So, vacuum is, we consider it to be lossless and unbounded, that is it has no boundaries, then for corresponding to every frequency omega there is a corresponding value of beta, and this relationship that we have between beta and omega, we already know how to get that relationship. Beta is actually omega into square root mu epsilon. Maybe in the earlier classes I might have used, instead of beta I might have used k, both essentially mean the same thing. These are the propagation constant. So, for every value of beta, you can even imagine this beta being a function of omega, because for every frequency of the plane wave that is propagating, beta of omega is given by omega into square root of mu epsilon. And for the free space, mu and epsilon are both constants, and square root of mu 0 epsilon 0 in that case will be the velocity of wave in free space, which is c. So, this would be equal to omega by v in general, or let me call this as Vp for reasons that will become very clear very shortly. Okay. So, from this equation that I have written, it is very clear what Vp should be. Vp is this parameter 1 by square root mu epsilon. It can be applicable for a homogeneous dielectric medium which is assumed to be unbounded, or it could be applied for free space wherein you will substitute epsilon is equal to epsilon 0. Now, this is the complex notation for the wave, as you might remember. So, this would be the cosine solution that I have. Of course, this solution keeps propagating all the way from minus infinity to plus infinity. So, let us say this is the wave that would appear at z equal to 0. So, this would be the wave at z equal to 0. This is the electric field. You know the units of electric field, you can write down the corresponding unit for that one. Now, let me arbitrarily assume that this is time equal to 0 reference. Okay, any point can be considered as time equal to 0 reference, because these waves extend all the way from minus infinity to plus infinity in time. So, I will arbitrarily choose this as 0. Now, what would be the wave at a later stage, right, at a later place? So, let us say at z equal to, in such a way that beta z is equal to pi by 2. Then what I have is cos of omega t minus pi by 2 would be the wave that would exist at the location beta z equal to pi by 2. So, this would be the case when beta z is equal to 0. This is actually the z equal to 0 plane, and for the case where beta z is equal to pi by 2, which I have taken arbitrarily, then there is a pi by 2 phase lag, as we would see, because the wave that would exist at beta z equal to pi by 2 plane would, I am drawing this on the same graph. So, hopefully, I am going to get the graph also right. Beta z is equal to pi by 2. So, it should go to a maximum here, and then it should go to a minimum here. So, this is a sine wave which I am trying to plot, but I am slightly struggling over here. So, let me actually draw it on a line that is below. Okay. So, that would be easier for me to draw. So, I have this line over here, okay, the same time. Now, instead of having the wave at this point at t equal to 0 being equal to 0, the value of this one will be when beta z is equal to pi by 2 at t equal to 0, omega t is equal to 0. So, you are looking at the real part of it. So, cos of pi by 2, which would be 0. So, what you actually have is a sine wave, right, and this sine wave would be the one that would be propagating for all times. So, if I were to hook up two oscilloscopes, one oscilloscope at z equal to 0 and the other oscilloscope at beta z equal to pi by 2 or z equal to pi by 2 beta, then I will see that the wave that would be there at z equal to 0 is slightly different from the wave at t. The properties remain the same. The wave at z equal to pi by 2 beta or beta z equal to pi by 2 will have the same polarization, same frequency, everything, except there is a fixed phase relationship the maxima that would be occurring at z equal to 0 is now shifted at pi by 2, right. So, or with omega t equal to pi by 2. So, this shift is what we call as phase delay or phase lag. So, we say that the wave at z beta z equal to pi by 2 is lagging with respect to the phase of the wave, or is lagging with respect to the wave at beta z equal to 0. So, this phase lag or phase delay, what would be the velocity of this phase lag? That is to say, if I were to follow this maxima, right, and then if I were to look for the velocity of this maxima, I will actually follow along the wave and then see how quickly this maxima is traveling along the wave. That would actually mean to take the argument of this Ex of zt, right. So, let me write down this in terms of the cosine thing, because we know that real electric fields will be will have a cos term actually, because it would be real part of this one. Let us not use the complex notation. So, if I look at this particular wave and if I want to follow the peak of the point, actually it can be any point that would be considered. So, it could be the constant phase point that I am actually looking at. So, if I were to follow this phase and how quickly, so how much time did it actually take to go from this maxima here to maxima at a different point. So, this is the velocity of this constant phase point, and this constant phase point velocity is called as the phase velocity of the wave, right. To obtain the phase velocity of the wave, I am going to follow the maxima, or I can actually follow at any particular phase point phi. Then I am looking at how quickly phi travels, which means that I am looking for d phi by dt, and if it is a constant phase point, the argument should be such that if I fix z and time t increases, there is a relationship. If both z and t increase, they have to increase together such that omega t minus beta z is always equal to this phase phi, right. So, this is the constant phase that we have considered, and that phase should be the same value, so that the value of the electric field will always be the same. That is what essentially means by looking at the phase velocity of the constant phase point, right. So, how would I be able to obtain, sorry, this is not d phi by dt, the velocity is dz by dt, right, how quickly this phase point is moving. So, for simplicity I will take this phi equal to 0, which means that I am following the maximum. Okay. So, since I am following the maximum, I can then now find out the derivative of z with respect to t, which will give me the phase velocity. So, differentiate this equation with respect to time, you get omega, because omega t differentiation with respect to time will be omega minus beta is a constant with respect to time. So, beta comes out, and then I have dz by dt, that would be equal to 0. But dz by dt is precisely what I have called as the phase velocity of this constant phase point. So, I seem to now have a relationship which says Vp is equal to omega by beta. Okay. And since beta happens to be for free space a parameter that would be independent of, beta would be linearly proportional to omega with this proportionality factor. So, we have Vp is equal to 1 by square root mu epsilon. So, this is the reason why I called this constant Vp as 1 by square root mu epsilon, because I knew kind of beforehand that this would be the velocity of the constant phase point for a single frequency wave which is propagating along the z direction. This is important, it is a single frequency wave having a frequency of omega. If you were to graph this beta versus omega, so let us say beta is here and omega is here, in some cases you will also see the axis interchanged with omega on the x axis and beta on the y axis. Both representations are equally used, widely used. We will also be using these two notations, so that you become very familiar with these two ways of visualizing omega and beta. So, for free space it is fairly simple, the relationship between omega and beta is obtained by inverting this. So, what you have is omega is equal to beta divided by square root mu epsilon, and clearly the ratio of omega by beta is the phase velocity which we have obtained. The relationship here is linear relationship, and at any particular point which corresponds to a frequency omega 0 and a corresponding point of beta 0, if you were to look at the slope of this line, or by finding the ratio of omega 0 by beta 0, the slope will give you the phase velocity Vp. Okay. And it is important to note that for free space condition and lossless condition, free space, lossless, unbounded medium, right, for all these cases or for the entire this case, the phase velocity is independent of frequency, right, independent of frequency. You might appreciate why this independence thing would be important if you were to look at this cos of omega t minus beta z argument, and we have seen that there is this particular phase lag. So, I can rewrite this cos omega t minus beta z in a slightly different way. So, let me rewrite this one by taking omega out. Now, I am just writing this part. So, I have cos of omega is taken out. So, t minus beta by omega into z, right. Now, beta by omega, omega by beta is Vp. So, beta by omega should be 1 by Vp. So, this entire thing can be written as cos of omega t minus z by Vp, right. This clearly indicates a travelling waveform with respect to time, but its phase velocity is Vp. If you remember your physics classes, this would be the wave equation for a wave that is propagating, having a frequency omega, having a velocity. At that point it was not specified what velocity you were considering, but this is actually the phase velocity. So, it is clear that the phase velocity happens to be independent of the frequency, and therefore, the phase lag that you would obtain would be the same for all frequency signals. So, if you change the frequency from omega to omega 0 or from omega 0 to omega 1, the corresponding values of beta also changes in a proportional manner, such that both the phase velocity as well as this 1 by Vp, which would be the phase delay, right, phase delay per meter kind of a thing. So, that would also be independent of frequency. These are really important concepts. The reason why this would be important is seen in the next case, where we are going to look at a situation where the phase velocity is not linearly proportional to or is not independent of frequency. The reason being beta is not linearly proportional to frequency. This is a situation where we have already solved this one for the waveguides, right. So, in waveguides we had this peculiar situation that beta was related in a nonlinear manner. So, it was equal to beta 0. So, I will use a bar over bar to indicate that we are considering beta in the bounded medium, right. Waveguide is an example of a bounded medium. I am continuing to assume that the medium is lossless, but I am indicating this bounded medium or the waveguide propagation constant by writing a bar over here. So, beta bar is equal to beta 0 into square root of 1 minus omega c by omega. Remember, omega is the cutoff frequency, and this equation of course is valid when omega is greater than omega c, that is mode is actually propagating, right. So, this would be the equation for beta bar, and if you were to sketch this one on say beta bar axis versus omega axis, right, you would see that until omega is equal to, as long as omega is less than omega c, the corresponding beta bar will actually be equal to 0. Since omega is increasing horizontally this way, I will consider this as the cutoff frequency omega c. Until this omega c, the value of beta will be equal to 0. Thereafter, it increases in this manner. Okay. For omega being very large compared to omega c, right, for a case where the operating frequency is so high compared to the cutoff frequency, then I can neglect this omega c by omega, and this would actually approach beta bar would approach beta 0, because omega c by omega can be neglected, its square can be certainly neglected, and therefore, the square root of 1 minus small quantity, that small quantity can almost be taken to 0, and this would be equal to beta 0. So, for very large frequency, there is a approximation, this particular beta versus omega curve will approximate the beta equal to beta 0 curve. So, in other words, the propagation constant becomes nearly the same as that of the free space propagation constant beta 0, which again is given by omega into square root of mu epsilon, where mu and epsilon are the constituent parameters of the medium that is used to form the waveguide. So, you have beta bar equals beta 0, which is actually omega into square root mu epsilon, and multiplied by a certain factor, and there is this factor which is making the relationship between omega and beta as non-linear. A slightly different way of putting the same thing would be to plot omega on the x axis. Okay. So, you plot omega on the x axis and you plot beta on this axis, and here you will see that until omega is equal to omega c, the cutoff frequency, beta will be equal to 0, and then it would go like this. There is an associated asymptote as well. Sorry, I should have curled this one slightly better. So, there is a corresponding approach to the asymptote as well. This would be the situation for the fundamental mode. What would be the beta versus omega relation for a different mode? Well, for a next mode, that would be like this. Okay. So, let us call this as omega C1, this as omega C2. This would correspond to the fundamental mode. For example, if this is a parallel plate waveguide, this would be TE1 mode, then this would be TE2 mode, and so on. For a rectangular waveguide, similarly the modes would be TE10, TE20, and so on. Okay. So, if your operating frequency happens to be anywhere here, so if this is my operating frequency, then only one mode exists, and for every value of frequency omega there is a 1-to-1 correspondence between beta and omega. Whereas, if the operating frequency goes over here, then for every value of omega there are two values of beta. This two values of beta indicate that there are two modes which are propagating. Okay. So, please keep these two in mind. Now, the primary problem that has happened here is that beta is now a non-linearly related to omega. It is not exactly the linear relationship that we were looking at. Okay. Now, what would be the phase velocity? If I go back to the same condition that the phase velocity can be defined as the ratio of omega to beta, I can still do that. So, I will be defining this as omega by beta, except that I am putting a bar over here indicating that this is phase velocity in waveguide. Similarly, beta is the propagation constant in waveguide. Okay. And if you now look at what is this relationship, beta bar is given by omega into square root of mu epsilon. So, maybe I can just try to find this omega by beta. So, when I do that one, what I will get here is square root of mu epsilon into square root of 1 minus omega c by omega whole square, right. So, this is beta is equal to omega, or beta bar equals omega into square root mu epsilon into this particular factor. So, if I take the ratio of beta to omega, so I will be pushing this beta bar by omega equals square root mu epsilon square root of 1 minus f c by f whole square, because omega c is 2 pi f c, omega is 2 pi f. So, for the corresponding frequency f, this would be the relation. So, beta by omega is the phase delay. So, omega by beta bar, which is the phase velocity inside a waveguide, will be given by 1 by square root mu epsilon into 1 minus f c by f whole square under root. This 1 by square root mu epsilon is nothing but the phase velocity of a wave if the medium would have been a free space, right. So, this would be the free space phase velocity V p divided by 1 minus f c by f whole square under root. What has happened here is that although there is a 1-to-1 relationship between V p bar, that is the phase velocity, and the frequency, as long as you are working in the single mode condition, let us say, that would be a 1-to-1 relation, but the problem is that V p bar depends on the frequency f. So, if my operating frequency is here, if my operating frequency is here, if my operating frequency is here, so for all these three different cases, the corresponding value of beta is different in such a way that the phase velocity will also be different. So, I should more clearly label this as the frequency dependent phase velocity, and this frequency dependent phase velocity is the one that would cause lot of problems. Okay. What would be the slope kind of a relationship? Let us say I am operating at some point over here. I know that corresponding to this there would be a corresponding beta bar 0, and this is the operating frequency omega 0. If I were to draw a line, okay, so this red line would correspond to that. If I were to draw a line and take the slope of this line, which would be omega 0 by beta 0, that would be the phase velocity V p. So, what I have obtained is the phase velocity V p bar. However, the actual relation between omega by beta, if I look at the local slope here, that would be different, and that local slope, if I were to find out by drawing a short line here and then taking the slope of this one, that will give me what is called as the group velocity V g. So, group velocity V g bar is given by d omega by d beta bar. Okay. Why is that relationship? Let us actually look at this case. Okay. So, let us consider that we have two waves, okay, one having a frequency of omega, the other one has a frequency of omega plus delta omega, both are propagating along z direction. Corresponding to this omega you have beta bar, corresponding to this one you have beta bar plus delta beta bar. That is, we are assuming that for a given omega there is a corresponding 1-to-1 beta bar, right. So, that is clear because this relationship is still 1-to-1 relationship, whereas for omega plus delta omega, where delta omega is a small displacement from omega, beta bar would also change only slightly, right. We will later find out what delta beta bar is. So, for this particular case, the two waves can be, assuming that both have the same amplitude and the amplitude is equal to 1, I can write the waves as cos omega t minus beta bar z, and because the total electric field must be the sum of both individual frequencies. So, I have cos of omega t minus beta bar z plus cos of omega plus delta omega into t minus beta bar plus delta beta bar into z. Okay. So, this is clear, the total electric field is the sum of one electric field component and the other electric field component. These two components have slightly different frequencies omega and delta omega. You would actually recognize, if I were to put one more term here and say, if I put this term as beta bar minus delta beta bar, okay, into z, if I have this electric field, then you would clearly recognize that this is the result of modulating this carrier and producing these two side bands. This would be the upper side band and this would be the lower side band, and then this electric field total would be called as the modulated wave, and this is true. You can actually call this as the modulated wave, and these modulated waves are the ones which actually allow you to convey information, because these side bands would then carry the information. If you were to just have the carrier, then there is no information, because if you fix omega, beta bar is fixed and amplitude is not usually considered here. So, there is actually no information being transmitted. If someone knows what is omega, beta bar and this one, or you can easily measured, there is really no information being conveyed with this one, because if you look at the frequency domain picture, the corresponding frequency here would be that of whatever the frequency omega that we have considered here, right. So, there is actually no spread around this omega, indicating that there is no temporal changes happening. This would be simply a boring cosine wave propagating all the way from minus infinity to plus infinity. When you have this situation, then there are side bands omega plus delta omega and omega minus delta omega, and the corresponding time domain waveform would be different, right. So, now you will have, in addition to the envelope, right, there would be carrier. So, you have this carrier and there is a corresponding envelope, and it is this envelope which is changing that conveys information to you. In a more general case, the spread will not be like this sinusoidal ones, but we will not consider that at this point. Okay. And for simplicity, that is for mathematical simplicity, I will assume that there is only carrier and its upper side band. Now, I can use some well known trigonometric identities to simplify this expression and write down for the total electric field as 2 cos omega delta omega t minus delta beta bar z. So, please verify this one, it is coming from cos A plus cos B formula, plus this is multiplied by cos of omega plus delta omega by 2 into t minus beta bar plus delta beta bar by 2 into z. Okay. So, this would be the total electric field. So, we have called this as E total of ZT, and now you can see two terms, right. On this term, the rightmost term, you have the frequency of omega plus delta omega by 2, the propagation constant is beta bar plus delta beta bar by 2. But we have assumed that this delta omega is so small compared to omega, and similarly delta beta bar will then be very small compared to beta bar, that I can write down omega plus delta omega by 2 as omega itself approximately, and beta bar plus delta beta bar by 2 approximately as beta bar itself. Okay. So, this is really giving me the carrier. So, I will now have the total electric field component being carrier. I am not writing what the carrier is, it is very clear what the carrier here is if you make these two approximations, times there is some envelope out here. What is this envelope? This envelope is cos of delta omega t minus delta beta bar z divided by 2. If I now look for how quickly the phase of this envelope varies, that phase velocity of the envelope can be obtained by setting again delta omega t minus delta bar z to a particular phase value, which I am going to consider as 0, and then differentiate this equation with respect to time. So, I get delta omega by delta beta bar dz by dt, which is now the phase velocity of the envelope. Please remember, this is a very different phase velocity we are considering. One hand you have a phase velocity of the carrier itself, that is given by omega by beta bar, whereas you are now considering the phase velocity of the, so this is the velocity with which the constant phase point on the envelope moves, okay, and this velocity of the envelope is called as the group velocity. Okay, so this is called as the group velocity, and group velocity is given by delta omega by delta beta bar, and in the case where delta omega tends to 0 or delta beta bar tends to 0 equivalently, this relationship is given by d omega by d beta, which is precisely the slope that I had talked about. Okay. So, these are the two velocities that you need to consider, and you need to understand that for the cases that we have considered, free space velocity V p is different. This would be equal to z c for vacuum or air. Okay. However, the velocity, the phase velocity inside a waveguide is different, and it depends on the frequency. There is also a corresponding group velocity V g bar, which is obviously a function of the frequency. Why? Because d omega by d beta is the definition for group velocity, and this particular case also shows that V g is dependent on frequency omega. In most cases, you have d omega by d beta to be less than 0, or you will have the situations where d omega by d beta is greater than 0. If this happens, this indicates that d beta by d omega is greater than 0, right, and this indicates d beta by d omega is less than 0. So, this particular case is called as the anomalous dispersion case, and this is called as the normal dispersion case, and the case for group velocity is normally defined very well for this situation. That is, for normal situation or for normal dispersion is where we can define very clearly what the group velocities are. The situation for anomalous dispersion is very complicated, so we will not pursue this anomalous dispersion case here. Okay. So, before leaving this group velocity point, I want to emphasize one thing which might normally cause confusion. If you look at the expression for the phase velocity V p bar inside a waveguide, right. So, this is inside a waveguide, I am emphasizing this again. You will see that there is term like V p divided by 1 minus f c by f whole square. Now, when f is greater than f c by f is a number which is smaller than 1, and a number smaller than 1 square is still smaller than 1. 1 minus of a number smaller than 1 is number that is less than 1, and square root of a number that is less than 1 is still less than 1. But the implication seems to be that V p bar of f is greater than V p, and if the medium of the waveguide or something is actually happens to be air or vacuum, right, then it seems that V p bar for a given particular frequency f will be greater than c. Now, how is it possible that something can have a velocity that is greater than c? You should remember that this is not really the velocity with which information or data actually is transmitted. It is simply a mathematical velocity or the velocity of a hypothetical phase point, and this hypothetical phase point can move at whatever velocity it wants. However, the actual information content is moving at a velocity given by the group velocity. You can see here, right. So, inside here the carrier is fluctuating quite a bit. So, which means that the phase velocity of the carrier would be higher compared to the group velocity, which would be the velocity with which the envelope moves. It will take a lot of time for the maximum of the envelope to move compared to the time where the carrier is fluctuating. So, it does not violate the principle of relativity, which states that no information can travel faster than light, and this is clearly the situation. Okay. It just because you get V p bar of f greater than V p, it does not mean that information is being transmitted. It is just a hypothetical phase point that is moving along with a given velocity. The information is carried by group velocity, and as I said, group velocity is a concept that can be nicely defined when you have normal dispersion. Let me just highlight couple of points before I leave here. In general, the information content will not be like a 2 sideband thing that I have shown you, but it would essentially be some sort of a spectrum which is spread around the carrier frequency omega 0, okay, which has a certain bandwidth of delta omega, and this represents the modulation. So, if this would be the envelope, and I call this envelope as A, and this would be A of omega, then this envelope A of omega would be centered around omega 0, which is where the carrier is, and the carrier is modulated to get this spectrum, and the time domain response A of t would be something. Okay. So, let us say this is the A of t corresponding to this one. It is not, but I am just considering an example here. So, this variation in time of the envelope is the one which carries information. So, these two are related of course by the Fourier transform, and if you were to look for what would happen if instead of sending just a sinusoidal waves, what would happen if I were to send this type of an envelope or equivalently this type of a spectrum, I will not go into the details of here. You can actually see that in the attached note that I will be putting in here. Okay. So, in the attached note you will see the derivation of this one, and you will see that the electric field component, this is only envelope. Okay. So, the envelope has to be multiplied by the carrier to become electric field, as you can see here, right. So, just the envelope is this A of t. So, you will see that the total electric field actually can be written as e power j omega 0 t minus beta 0 bar into z, which would be the carrier moving, and the velocity of the carrier is the phase velocity V p bar, okay, times the envelope will be a delayed version, assuming that this is a lossless medium. The envelope will be a delayed version, which is given by t minus beta 1 bar into z. Now, what is beta 1 bar? Beta 1 bar is the shorthand notation for del beta, which implies that beta can be a function of omega as well as other parameters. So, this would be del beta by del omega evaluated at omega 0. So, this would be evaluated omega 0, and this is equal to 1 by V g bar. Remember, V g bar is d omega by d beta. So, d beta by d omega is 1 by V g bar, and this is the delay, or the velocity of this one would be the group velocity, and the delay will be the group delay. Delay is 1 by V g bar. Okay. This would be the group delay, and the envelope arrives at a later time, which is determined by the group delay. As I said, these concepts are very well defined for normal dispersion case, and for the case where your propagation constant happens to be linear, I mean one-to-one function. That is, if the operating frequency is taken to be such that the waveguide is essentially single moded, then all these concepts that we have discussed will be sufficient to understand the phase and group velocity. These concepts need to be defined in a much more rigorous way when you go to anomalous dispersion, or you go to the situation where you have multiple operating frequencies. Okay. So, this is the phase velocity and group velocity. Let me just remind you that anomalous dispersion case, the wave actually the information in the form of a pulse is used to compress the pulse. So, anomalous dispersion leads to pulse compression, whereas normal dispersion leads to pulse expansion. More rigorous way and much more details of this one can be found in the literature or in the attached note. Please take a look at the note. Thank you.